Uh, Jim is always a hard act to follow. When we first put this seminar together and gave it, it's been, I don't know, 2-3 years ago now in Baltimore, AISC made arrangements for a couple of people to come in and audit and critique the seminar. And one of the individuals made a comment. He says, Fisher is entertaining, Kloiber is factual. I think that in kind way of saying I'm boring compared to Jim. So we'll see what we can do to keep things moving along here. We're going to start talking about columns, and this looks like a series of local buckles here. Actually, this is one that Jim had taken out of a building that had a magnet crane handling scrap. And of course, what happens is they drop the magnet into the scrap, and then they pull it up, and it's like pulling out tiddlywinks, and you got pieces hanging every which way, and it slams into the column, bends the columns all up. In this particular case, the fix on this particular column was to try to do some limited straightening and repair of the flanges. Then they boxed it with plates across it, encased it with concrete, and put guard angles on it. And so then after the concrete would get beat up and the guard angles started coming off, they could repair it that way again. It's just a comment that Jim refers to these buildings with magnet cranes as sort of self-destructing. But we're going to talk about maybe more practical situations. I want to talk about column splices, where column splices do not line up. You have gaps. And AISC says that if you have a gap of a 1/16 or less, it's okay. You don't have to do anything about it. If you have gaps that are more than a 1/16, you can shim, and I believe it's up to like 1/4 of an inch. And you can use just flat mild steel shims. You don't have to use tapered shims. Force them into the joint, probably tack weld them if you want to make sure. We had a building, 20-some story building that we were doing a few years ago, and we had some heavy 14-inch columns that had some gaps, and we put the shims in, and they were in about probably the 4th level or something like that, the 2nd tier. And by the time we completed the building, the shims were almost squeezed out of the joints, so the joints closed up and it really wasn't a problem. If you have problems where it's hanging up on the splice plates, you might have to remove the splice plates and replace them. You may perhaps just simply field weld them if they're bolted. And the idea is you want to try to use simple splice plate details and use standard AISC splices. We're talking something that looks like this. As a fabricator, one of the things you're going to hear from me is nowadays fabricators like to put holes. They've got all kinds of hole-making equipment. We have CNC punches, we have CNC drill lines, and so it's relatively easy for us to do holes. It saves the layout and stuff like that. And so we use a lot of bolted have there's common sometimes to weld this one, but the nice thing about a bolted detail here is that you'll have a little more adjustment in this connection, a little easier to get the upper shaft in if these bolts in here are loose. Typically these are shipped with just a couple of shipping bolts in them. We may even lay these plates back so they don't get bent up. One of the other things we're pointing out here, as you notice this here, we're saying that the splice typically should be 48 inches above top of concrete. The reason for that is OSHA requires us and the erector to put in safety cables around the perimeter and any interior openings where the cable is at 42 inches above top of floor. And so if we have a 48 inches above top of concrete, we can put a hole in up here, and that serves a dual purpose. It'll serve as a lifting hole for the column. The nice thing about it, you can stick a pin in there and a shackle on it. The erector can hang that column. It'll stand up vertically. He can put a lanyard on there to pull the pin without even sending somebody up the column if he wants to. Very safe. And then we can use that same hole again for the safety cable around the perimeter. If the column's oriented the other way, you might have to end up trying to get a hole in here somewhere, or you can weld a nut on the perimeter, which is what we used to do. But these are required to be done in the shop now. You have to have holes for these cables in the shop, so it has to be a detail. So we're saying we like to see at least a minimum of 48 inches above top of concrete to splice. We're talking about gaps, and there's several reasons why you could end up with gaps in here. First of all, when you're sawing these things in the shop, particularly if they're a heavy column and you're sawing them with a bandsaw, you might get a little bit of drift and you might get a little hollow here in the web. You know, it's possible also to get a little bit out of square, although you should be checking that in the shop. The other thing is that when you go to plumb these things, you know, if there's a little variation up on top here, these things will open up simply as you're doing your fit up on your erection, and so you may end up with slight gaps in here for that reason. One of the things you should do, we always try to tell our erectors, if you see a problem, you know, give us an early advance notice of it. We had a project back a couple of years ago. It was I think it was a 6-story building. Anyway, we were on the upper tier of the building, fairly large footprint with maybe 50 columns in the footprint. We got a call late in the afternoon, and they said that every column in the upper tier, they told us, was hanging up on the splice plates, and there was a gap in here, and they needed fill plates on it, shim plates in there, and they needed them rush because supposedly they had not only the upper tier all in place, all detailed out, bolted up, decked, but the contractor was ready to start pouring concrete the next day. I mean, why would they take that long to notice this problem? Well, it turned out there were only a few columns like this. But again, you got to try to impress upon the erectors that if they spot something that's not quite right, to at least make an inquiry. And we'll see some other examples here that way. Oops, sorry about that. Okay, you've got a problem with your columns too short. If you're fortunate enough that it's a first tier column, you might be able to simply grout, change the grout in the thing, provided you've got anchor rods that are long enough. You know, you'd like to have, say, an extra inch or so an anchor rod length minimum so that you could adjust height if you needed to. You could add more grout. You might be able to take that splice plate apart, put a shim in between it, and then use different splice plates. If you know about it early enough, you may be able to replace the column, particularly if you're off by more than an inch or so. Otherwise, more than likely, you're going to modify the beam connections to correct the elevations. You're probably going to either use some sort of a welded connection and then maybe relocate holes or simply weld the connection. Prevention, you want to try to use uniform base plate elevations where possible and clearly note any exceptions to elevations. Clearly show the elevations at the tops of all columns so you can see what the roof slopes are and so that the column heights are detailed right. And then the shop should provide proper quality control to make sure that the dimensions are right on the columns. This is an example of a project that we had, and this particular column was erected an inch too low, and we were notified about it at this time when it was all, this column actually runs down all the way in that concrete wall. So there wasn't a lot we could do about the column anymore. Fortunately, this was an industrial structure. This is a big incinerator in here, and there was really no architectural concerns about appearance, and we were able to come along and weld an additional plate on top of the edge plate here and pour an additional inch of concrete on that edge of the slab, adjust it that way, and then modify the connections up above. You see up above what we did is we simply modified the connections, raised them up, and welded them in place. We had a similar problem, very much like that one, about 2 bays down, and in that particular case, the forming was in place, but the concrete wasn't done yet, and we were on site about 10 o'clock in the morning, talked to the erector, talked to the general contractor, got on the phone with the engineer of record, and on that one we decided that we needed to raise the beams on that floor because it wouldn't work putting that plate on like that. So we immediately did a sketch which we faxed out to the engineer of record, and by the end of the day the erector had gone in, modified all the connections on that other column, and the next day the contractor was able to place his concrete in all the forms. So it's one of these cases where Jim was talking about where it's important to move quickly to avoid delay. The problem we had, there were 6 columns on this job that were set an inch too low, and there was a detail error caused on the design because the design drawing changed the base plate grout thickness on one detail. Base plates, where possible, should be the same, and if there are any exceptions, you should clearly flag them. We had another case in this situation where we had, it was a brace bent, and one column was an inch too low. The erector erected the brace bent, and I think there was 4 or 5 levels of diagonal bracing. None of the diagonal braces would make. They had them all just sitting there, their angle braces, and they poured the base of the column into concrete, never notified us, that there was a problem on fit up. So what happened is we had to come back, cut the concrete out, raise the column up an inch, then all the braces fit. But there was an obvious problem, and nobody notified the engineer of record or the fabricator about the problem. So it's important to have timely notice. Column too long. You can use less grout. Again, if you're fortunate enough that it's on the first level. You can modify beam connections, which is more than likely what you're going to do. If you're talking maybe an inch or 2 variation, something like that. Again, if you know about it in a timely manner, you might be able to replace the column or perhaps remove a section from the column. If you've got a first-tier column, quite often what you can do is you can cut the base plate off and cut whatever you have to take out, whether it's a foot or more at the bottom off the column, and then turn your base plate over and then re-weld it. Now, since you don't have a finished cut on that column, you should design that weld to take the full axial load of the column. But that's one solution to it. Column not plumb per AISC code of standard practice. First of all, you'd like to find out why is it not plumb. I mean, are the anchor rods out of position? As some of the beams that are framing to it perhaps detailed wrong or fabricated wrong? You'd like to be able to correct the problem properly. But so you may have to remove or adjust the beam connections. You perhaps cut the anchor rods and move the column, replace the anchor rods with epoxy rods. You might be able to leave it as is and brace the column. AISC has this requirement of L over 500 for column plumb, but a column is really a compression member, and it really doesn't care in what direction it is as long as it's braced to handle any eccentricity in the column. So if there is no architectural problem, you don't have a cladding problem or some other fit-up problem, you may be able to tolerate something more than L over 500 provided that your stability is okay. So that's something you could look at. And this may be another one of those cases where a fix isn't required because you've got enough stability either because of shear walls or bracing or whatever you have. So you may be able to leave it as is. The important thing here is the erector should check the anchor rods and of course plumb in a timely manner. We have found this problem occurring on more than one occasion in large footprint buildings, like big box structures, where you're using joists and joist girders. The problem is that the joist girders and the joists all have slotted connections in the ends of the joist girders. And if the erector's out there going like crazy, as they are often, they're going across the building, and if they're not checking plumb, and they get out there, 3, 4, 5, 6 bays, they can be several inches out of plumb at that point. And at that point, it's difficult to go back and try to pull all that stuff out. So it's important, and really OSHA requires it, that you, every couple of bays, that you brace and plumb your structure as you go so you don't allow the structure to get out of tolerance that way. But like I say, when you have slotted connections, if you don't plumb as you go along, you can get into some serious problems. After erection, the beam line's too short, and we're talking here welded connections. If you have a full moment or a CJP welded moment connection, and it's a fairly large member, you could get shrinkage of approximately 1/8 inch in that joint. And if the solution to it is cut loose several connections and correct by weld build-out per AWSD 1.1, and then provide adjustable erection connections and plan for welding to compensate for shrinkage. We had a project that we did, again, the same 20-story building that we did, had sort of a unique system to it in the fact that it had the lateral system was a series of Virendale moment frames on 3 faces of the building, and the loads were such that in the first 3 levels, the moments in the Virendales were large enough that the only way we could take the moments or develop the moments in the beam to column connection was with complete joint penetration welds. We had 36-inch wide flange columns and 36-inch wide flange girders, and above that the moments went down enough that we were able to do it with end-plated connections. And we got a call on the first side, we got a call from the erector when he was at the 4th level, and he said, your beams are too long, I can't get them in. And you'll see in here that when we detail end plates, we detail them short. And we couldn't figure out what was wrong, but we had a suspicion, so we asked him to tape the building. And I think in about 165 feet, he was like 2.5 inches short on his building. He had not compensated for the weld shrinkage on this thing, and he had sucked this whole building in. He had to go back and cut loose a number of these connections. And like I say, AWS D1.1 has certain joint configurations that you have to have. They're detailed dimensions and they're pre-qualified joints. And depending on the slope of the the surface, you have a certain root dimension that you can allow. And if you exceed that root dimension, what you have to do is you have to build out that joint. The concern that you have is if your root is over, say, 3/8 of an inch, and you try to bridge that with one weld pass, you're going to get shrinkage in there and tend to have a cracking. So what AWS says is that when you get over a certain size, you have to lay a pass on one side to reduce that gap down to what their requirements are, and then you can put the closing weld pass in. And that's the type of corrections. AWS does have limitations on the amount of correction that you can make, but they do allow, and we'll talk about this some more, they do allow the engineer of record to accept a larger correction provided there's a procedure developed. But anyway, on this first side they had to cut loose several joints. On the second side, I think they ended up cutting out 2 joints. By the time they did the third side, they had no problem whatsoever because they learned how to compensate for the shrinkage. I mean, ideally you'd like to be able to rough erect the whole line and start at the center, plumb the center column, and then just keep leaning your columns out, and as you weld them, compensate for the shrinkage. If you have to start on one end, you've got to plan on how this shrinkage is going to affect your structure. It can be done, but we don't up in this area do that many full welded moment frame structures, so the erectors may or may not have the experience with it, and that's something you have to be a little concerned about. After erection, the beam line is too short or too long. If you got end-plated connections, if it's too long, of course, you have to remove the beam and refabricate, and that's a real painful process. You know, it basically has to go back to the shop and probably have that end plate cut off and a new one put on. So you want to try to detail them so you come up short, and then you can provide finger shims to adjust for it. We typically detail end-plated connections, moment connections, an 1/8 inch short on each end. Now again, in both of these welded and end-plated connections, you know, you got to keep in mind what sort of a project you have. I mean, if you got 1 or 2 bays, who cares if you're a little short, you're a little long? You can live with that in your structure. What you're worried about is when you have several bays, or perhaps you have tolerance requirements at the ends that are very critical. Then you need to compensate for these things and take provisions to adjust for them. I want to talk about camber, and we'll talk about members to camber, and maybe some non-composite beams, perhaps some long span roof beams that you want to camber to make sure that you're getting slope on them properly. But you know, the vast majority of the beams that we camber nowadays are composite floor beams. It's, you know, we camber these things anywhere from 1 inch to 2.5 to 3 inches, and it's very common. And so that's where most of the cambering occurs. Trusses, we've always had arrangements to camber. If you have continuous WT cords, generally you can bend that camber in when you fixture the trusses and provide whatever camber there is for it. If you have wide flange cords, generally you'd like to do the camber, you'd like to have straight cord sections and segment them so that you would provide the camber by changing the slope at panel points within the truss. And crane girders that are greater than 75 foot. There are not many of us that do crane girders that long, but these are some in the range. Jim's done some over 200. This is an American Iron and Steel Engineers recommendation, and you'll see that the reason they don't camber the smaller ones is because the girders should be stiff enough, and the slight deflection that you're going to get where the crane might have to run uphill is not a problem. Members not to camber, we got beams with moment connections, spandrel beams supporting fascia, and beams with torsion loading. Now there's something that these three types of beams all have in common, and that is that these beams typically require connections to the flanges. And we'll talk about why we don't like to camber members that have connections to the flanges. We talk about continuous beams with cantilevers. The problem there, of course, is that in your backspan you'd have what we'd call positive camber, and in your cantilever section you'd have negative camber. This is difficult and expensive to do. We do this in continuous girders for highway bridges, but I don't think you want to pay the type of price for building structural that you pay for highway structures. So generally these beams would be stiff enough and you wouldn't need to provide camber in this type of structure. And beams with bracing connections, again, obviously if you're going to do cambers, you're going to create problems in your bracing connections and your fit up of your bracing connections. And normally if you're using, for instance, a chevron type brace, your girders are going to be stiff enough that you're not going to need cambers in them. And like we said, crane girders less than 75 feet. Going on, beams with significant non-symmetrical loading. We're talking typically transfer type girders, and the problem here is that if your non-symmetrical loading is, say, off-center, well, it would be to be non-symmetrical, obviously, and closer to one column, it's very, very difficult to provide camber, a non-symmetrical camber diagram. Particularly, we're going to talk a little bit about how camber is put in the shop typically. And if you've got something like a transfer girder, you can accomplish probably the same type of effect as you would with camber by simply, perhaps if you've got a column on top of it, either shimming or increasing the detail length of the column to compensate for when dead load deflection. You might even do the same thing with some of your floor beams into a big plate girder. You might adjust your elevations, your connections to provide the camber in your floor framing without having to camber these big heavy girders and things like that. Beams less than 25 feet. Okay, the reason for that is that the vast majority of cambers nowadays are put in the shop in the mechanical press. And the mechanical press is a big frame, and it has two reaction points that are approximately 25 foot apart. And internally, at about 6 to 8 foot apart, you have two big rams. And so you put your beam in there, these two big rams then shove that beam till you shove it through yield and it takes a permanent set. If you've got a long beam and you've got a fair amount of camber, you may move that beam and hit it in 2 or 3 places to get an approximate circular camber. The amount of camber you're getting in the camber diagram shape is really not critical. As long as you got your mid-ordinate right, you know, whether it's a parabola as it theoretically should be or a circular camber, it's really not going to be that significant when you go to place concrete on it. But the idea is if you're less than 25 feet, it probably won't fit in the camber machine unless somebody has a different style machine. And if you have to go to heat cambering it, the price of heat cambering goes up by a factor of 4 or 5 you know, what it takes to mechanically camber. So you'd like to stay away from having heat cambering requirements. And besides that, if you're less than 25 feet, the amount of camber you're talking about, you know, is probably pretty minimal and maybe not a requirement, big issue. Maybe you can up the beam a size or two, and it'd be better to do that. Also, you've got beams with webs of 1/4 inch or less. And one of the problems that we see is that a lot of people out there are using programs like Ram Steel. And some of the people that are relatively new to design will go out there and plug this stuff into Ram, and they will come up with some 12-inch 14s or something like this that work structurally, you know, and then they have cambers in these members, you know. And what happens is if you have webs that are 1/4 inch or less and you try to force that beam into yield, there's a good chance you're going to cripple that web. And so you almost either have to upsize the beam to avoid that problem, or you have to put it in with heat. So we're saying if you have these real light beams, try to avoid cambering them. Beams which require less than 1 inch, again, we're talking about just simply economies. If you've got a 1/2, 3/4 an inch of camber, I mean, are you really going to be placing concrete that accurately, predicting your dead loads that accurately? You know, so economically, what we normally would like to see, you know, we see a lot of floor beams. You're talking 30 by 40 bays or 40 by 40 bays. On a 30 by 40 bay, you know, you may have 18-inch girders or floor beams that are taking 1.5 inches, 2 inches, 2.5 inches of camber, depending on your loads. And that's really no problem putting them in. But your girders in there, you're loaded at the 3rd points typically. And so, you know, if you have 3/4 inch camber out in the middle of it, you're talking about we're getting maybe 3/8 of an inch or 1/4 inch where the floor beam frames in. Is that really that critical, you know, to your elevations and stuff like that? And so if you can avoid cambering your girders and just camber your filler beams, there's some savings involved there. We're talking about when to camber or when is camber performed. And again, we talked about the fact that fabricators now have these fabrication lines where what happens is we take steel in from the mill and we run it through a saw and we cut it to length and we cut it square on the ends to the uncambered line on the member. We move it over to another line where we run it through a punch or a drill press, and again, we like to run that through uncambered because it's a lot easier to run it through uncambered, and we punch it and punch the end connections and all the other connections when it's straight. And then we send it to a cambering machine and we camber it, and what happens are end connections like this go like this, you know, so we've got a little end slope in our members. This is why we're talking about when you have to make connections to the flanges, we don't like to see cambers because that creates some problems. You almost have to, when you're doing connection, if you're going to do that, you'd have to camber the member first, then run it back through, and with the camber in, try to square up the ends and cut them. It's much more difficult. And usually, if you're doing end connections and you're going to make, you know, fascia beams and torsional members heavier anyway, camber is normally not required. So that's why we're saying not to camber those types of members. So we're saying beams which require square and parallel ends for connections such as end plates, welded moment connections, or flange connections for torsion, that we recommend not to camber. Too much camber. The problem we've got, if you got too much camber on the thing, you can perhaps compensate by pouring less concrete. The problem you would have to be concerned about is make sure you have enough thickness of concrete to still get your fire rating. You might be able to replace the beam. You might be able to remove the camber, which is easy to do in the shop but difficult to do in the field. Generally, if you've got too much camber and you've got it up in the field by this time, you're going to have to do something in adjusting the concrete depth and the concrete placement. But the prevention generally is to specify camber properly and to camber only for concrete dead load. And do not use camber unless necessary, and design beams with extra capacity rather than camber to handle special conditions. And the important thing here is that camber should always be checked in the shop. And the AISC Code of Standard Practice talks about this, and we'll talk some more about the Code of Standard Practice requirements that says that camber shall be checked in the shop in the unstressed condition. Once you get it to the field, you really can't check anymore. You can make sort of a spot check, but there can be arguments about it. And at that point, it's difficult to handle any problems. So it's more important, if you're concerned about your cambers, to have them checked in the shop and make sure they're checked in the shop.